Good morning, my dear students. Welcome to today's session. Uh, After dealing with that two hinged arches with circular geometry and parabolic geometry, we will now see the temperature stresses in two hinged arches. Okay, so if uh, either concrete or steel arch, you have if the temperature is increased or decreased drastically, if the change in temperature is uh, a bit high, then you will find some additional stresses due to temperature other than the gravity loads. That effect of temperature changes on two hinged arches we will see now. So let us take the two hinged arch where you have hinge at A and hinge at B and no hinge at the crown, right? So you have already studied related to the temperature stresses when a bar of L span L, if it is increased by temperature is increased by T degree centigrade, uh, what could be the change in length, what will be the stress developed in it. Okay, so that information you have with you. You just recall it once, how the temperature stresses are being calculated. Okay, so one thing that it has to come to your mind that temperature stresses develop only when you arrest the uh, change in dimension of a particular member when temperature change. For example, if you have a bar where one end of the bar is fixed, say, right? If the temperature of this bar is raised by some T degree, okay, right, T degree centigrade, there won't be any stress developed in this bar. Reason, the dimension of the bar is free to expand due to temperature. The length of the bar, you set it free for elongation. Okay, hence there is no resistance offered by the support for or against the change of the dimension. Okay, right? Hence it is free to expand. Hence no temperature stresses develop when you have any free expansion possible. Got it? So that is what you have to observe when any member is increased, its temperature is changed by some T degree centigrade. If it is having restraints for change in dimension, then only you expect stress development. And you know how much is this delta value. So delta due to temperature is L alpha T. Okay, so this is now the formula for calculating change in dimension of a particular member where the temperature change is involved. Okay, So alpha, the thermal coefficient of expansion, okay, and L is the length of the member. So this is how you measure this delta. I think you recall everything regarding this, temperature stresses. Okay, right. So what happens when this end of the member is also fixed? Okay, now what? You are increasing the temperature and there is no provision for the member to change its dimension. So how much you are stopping this, you are stopping the elongation of the bar, because I am talking about temperature increase here. So what this support is doing, it is offering this resistance. We, let us say, call it R. So this is the resistance from the support, because the member is trying to elongate and the support is not allowing it. So that's why you expect this much force acting on this bar. So the stress in this case, because it is axial, so load by area, R is the resistance, and this is A, cross sectional area. So this is the in case of axial loads stresses, right? So this is the very brief information related to this temperature stresses, right? So you recall, you go back to your temperature stresses chapter and recall it from fully from what exactly you have studied, right? So this is what is required to understand this topic. Okay. So now we are talking about arches. What happens when temperature change? If this is the arch and without A and B, what would have happened if the temperature is changed? You expect the arch to, know, become like this. Okay, got it? If you increase the temperature of this arch, okay, by T degrees centigrade, got it? So it would have been like this. Okay, whereas you have support A, support B, which will not allow the arch at A and B to move outward. You see, because of the temperature change, support A, support B, the 2 points on the arches are trying to move outward. Okay, whereas what the supports will do, they will try to stop that movement. So that is what is this uh, horizontal reaction is expected because of temperature change. This H is not because of the loads. Okay, this is just because of the temperature change. So how much this will be, right? That is your no calculation now. So loads will cause some horizontal reaction. If there is any temperature change in the arch, that also going to create a horizontal reaction. So why not vertical reaction and all? Because you see, the length change, what we are talking about, okay, because of this delta arrested length change, so the force that is acting along the length is H, right? So this is span direction, this is direction of the span. Okay, so the change in length that you are arresting here is in the direction of H. So the equation that you are going to use it here, the application of strain energy equation. So dou u by dou u by dou h, Castigliano's theorem, will give you delta value. Okay, got it? Whereas if you use vertical forces also present here, wherever you have vertical forces. Okay, so this movement in vertical direction is not there, it is zero, because this is going to hold this position. Okay, so vertical movement is not expected, right? So only considerable horizontal movement is expected from the support points A and B and the change in span. So that is why we are now concentrating on the direction of the force in which the change in dimension is happening. Right. So that is what is now is written here. I'll just uh, clear it off. Right. So dou u by dou h from Castigliano's theorem, uh, dou u by dou h is equal to delta. Means what? Uh, Partial derivative of strain energy with respect to any force will give you displacement in the same direction. Okay, so that is what is written here. uh, Delta is now replaced with what? L alpha T, which is change in temperature because of the temperature change, right? Okay, so dou u by dou h is equal to delta. This is how it has come. Okay, so this is by Castigliano's theorem. You are well aware of it, which is studied in the uh, strain energy chapter, right? So now what to substitute for strain energy? Okay, so strain energy, because of bending we are talking about, we will take only strain energy due to bending. There will be three forces developed in the arch that you are well aware of. The three forces developed in the arch are normal thrust N, radial shear Q, and bending moment M. Out of these three, bending moment M is the major contributor other than this N and Q. So that's why, and even bending moment is critical for arches for design purpose also. So hence we will concentrate on bending moment. So moment strain energy due to moment is already we have expression for it from the strain energy chapter, integral mx square ds by 2ei. So what is mx there? Okay, remember this is only due to temperature change, not because of the gravity loads. Okay, so if you have only temperature change, if there are no loads at all, what is va and vb value? Va is equal to 0, because sigma fy, if you apply, there is no vertical load at all, so we don't expect any you know, vertical reaction. So that is the point why va and vb are zeros. Okay, so va vb is equal to 0. Okay, so take a section anywhere on the arch at a distance of x. Okay, so sum of all moments to the left is h into y. Okay, so it is anti-clockwise. Left anti-clockwise is minus. So mx is minus h into y. So substitute this u in this fundamental expression for the relation between change in dimension to the force in the direction. That is by Castigliano's theorem, right? So uh, dou by dou h of replace for u is what? Integral mx square by 2ei ds, which is equal to L alpha t. Okay. So now you separate all those constants and integrable terms. Okay. So substitute for what? Mx now. We already have mx expression. So what is mx minus h into y whole square, mx square by 2ei ds divided by dou h is equal to L alpha t. Okay. Right. So now what? Sending the differentiation inside the integration. Okay. So 1 by 2ei is constant term. Let it be there. So dou by dou h of, okay, you have to look at it like this. Dou by dou h of minus h y whole square. Okay. So what it is? 2 times minus h into y. That is what is written here. And dou by dou h of minus hy inside the braces, differentiation for this term. So it is like dou by dou x of minus some y into x. Okay, right? So that h is the variable now. So others will be constant. So what it will be? Minus y into dou by dou h of h. Okay. So dou by dou x of x, how much? 1. So minus y into this value will be 1, right? So that's why minus y has come, and ds divided by 2ei L alpha t. Okay. So this is how this is being differentiated. Okay. Right. So finally, you have the formula for the h. Okay, keeping all other terms to the other side of it. Maybe you send all the terms to the right hand side, so you have the expression for h. You see to the right hand side what you have? L alpha t, and so this is to the right hand side. So h you keep it aside. So what variable you have? Y is a variable, and here it is y. So minus of minus plus, and 2 and 2 gets cancelled. So integral y square ds divided by ei. Okay. So here you don't have anything to cancel out ei. So flexural rigidity remains in the equation. Do remember, unlike you have h expression for gravity loads, where numerator is integral m dash y ds divided by ei. The same ei is present in the denominator. That's why we are able to cancel out. But here numerator is different and denominator is different. That you have to remember. So numerator value is L alpha t, that is delta L, change in length of the span of the arch. Okay. And denominator is like integral y square ds, the same as the earlier expressions for gravity loads, but you have divided by ei in this expression. Okay. So this is what is the formula for finding horizontal thrust developed due to temperature change alone. Okay, what happens if you have loads also on this arch? So if I apply some load on this arch, what happens? So this is like a W per meter. Okay, what happens? You will have H also from loads. Okay, so you have H from temperature, so both temperature and loads. Okay, so what you have? You have H developed from loads and also from the temperature change. So if you observe, both are in the same direction. Okay, so let us discuss this in a bit now extensive manner. So what happens when you have loads as well as a temperature increase? What happens? So if temperature increase is there, your H value from loads is adding to, or H from temperature change is adding to the H from loads. So what is happening? H is increasing. Horizontal thrust is increasing. Okay, when horizontal thrust is increased, what happens to bending moment? Okay, so mx at any point in the arch is equal to what is like? It is m dash minus h into y, right? So if h is increased, what will happen to mx? It will reduce. So the effect of temperature increase on two hinged arch is to reduce the bending moment in the arch. So it is a desirable effect, right? Okay, we want bending moment to be reduced. Okay, so when temperature is increased, bending moment is going to reduce, whereas horizontal thrust is going to increase. Similarly, what happens when temperature is reduced? So the horizontal thrust will have opposite sign here. Okay, the horizontal thrust at A and B will change its direction, because what? The arch is going to shrink. Okay, will try to shrink. A and B will try to move inwards, shrinking, whereas the supports will try to apply force away from A and B. So opposite. So opposite to H. So because of that, H will reduce. And because of that, mx is going to increase. Okay. So this is a clear analysis of what happens when temperature is increased and what happens when temperature is decreased. So the effect of temperature increase is desirable. Okay, means what? uh, you will have a safety, because you have already designed for mx. If you have designed an arch for the loads, and if you observe there is a temperature change, when you will not bother about temperature change, only when temperature is increased, uh, you have already designed for some value of bending moment that is going to reduce, so no problem, you are in safe side. But when you have to worry about the temperature change, when temperature is decreased, you have already designed for some bending moment in the arch. Okay, and now the bending moment is increased. So if you have designed for 100 kilonewton meter, because of temperature change it is going to be say 150, then you have to worry about it. So which is a critical effect? Temperature reduce is the critical effect, and temperature increase is desirable. Okay, so safety, you have safe side, whereas temperature reduce is critical effect. You will be in critical condition. Okay, means in danger, right? So only that you have to check out with the factor of safety that you have already applied for, how much you are losing the factor of safety. It's all practical aspect of it. Okay, so you have designed for some value, and later point of time you observe temperature changes are heavy, and then you have to calculate what will be the change in bending moment, whether is it in allowable limits or not. The factor of safety that you have used, is it within that factor of safety limits, or it's going beyond. Okay, all that is as an engineer you have to worry about a lot when you are checking its safety or critical condition. Okay, so finally you are able to calculate horizontal thrust from temperature change by this formula. Numerator L alpha T, and denominator is integral y square ds by ei. It is same as the denominator is same as the earlier derivation for h due to loads, where numerator will be integral m dash y ds by ei, divided by integral y square ds by ei is the denominator. So denominator same, only the numerator part is changing. Okay, so that is to incorporate the temperature change. Okay, so got it. So we have started with uh, the Castigliano's theorem, where dou u by dou f is equal to delta. Okay, that is our basic principle of Castigliano. If you differentiate partially the strain energy in any member with respect to force, that will give you change in dimension in the same direction of the force. Okay, so that we have applied here, and then we have substituted for strain energy due to bending, because it's going to be the critical effect among all three, n q m in the arch. Okay, so we wrote expression for mx, which is minus h into y, because you don't have any loads taken there. Okay, so because loads can be separately dealt, and you can add that h value to this. Okay, right. So substituted for u, and then simplified, differentiation sent inside, and then finally you have this final expression h because of temperature change is equal to L alpha t divided by integral y square ds by ei. Okay, so you can find the h value separately from loads and separately from temperature change, and accordingly you should add or deduct, because when you have to add h and h due to temperature, this is I can now have to have a different notation for this. So final or total h if temperature is there. So h due to loads and plus h or minus h due to temperature, that I have to perform when you have both loads and temperature. So when you have to use plus, when temperature is rising. Okay, when you have to perform minus, when temperature is reduced. Okay, so this is how you find final h value, and all remaining calculations, once you find h value, and how to find n, q and m anywhere in the arch is going to be very similar to taking a section and working out with the earlier derived formulas. Okay, so this is how we estimate temperature change effect in case of two hinged arches. Okay, as the discussion has come about temperature stresses, Let us discuss what happens when you have a hinge at the crown. Because of temperature change, what happens to a three-hinged arch? And you see, if you have an internal hinge in any member, it will allow free movement or free rotation, in the sense I can say. So when you have increase in temperature, okay, so the hinge is going to allow a free movement of the member. You need not now worry about uh, the force coming on to A and B. Okay, right? So this is how the effect is going to be. Okay, so you don't expect any force applied additionally at A and B due to temperature change. Okay, so that's why we don't expect any horizontal thrust developed at A and B due to temperature change if it is a three-hinged arch. The reason behind is very simple. I have explained it at the initial point of time that when you stop the dimension change, then only it is going to, if you do not allow free movement of the member, then only it is going to cause any reaction, okay, or resistance. So there is no resistance developed in case of three-hinged arch, because the hinge available at the crown point will allow the arch to expand or contract freely. Okay, so that is the reason why this H will be 0 due to temperature, because of temperature changes in case of three-hinged arches. Okay, that's why we did not discuss anything related to temperature in three-hinged arches. Only the discussion has come in two-hinged arches, right? So this is how you have to uh, see the temperature change effects in the arches. Okay, thank you.